Today we are entering into finding derivatives of multivariable functions called partial derivatives. So let me give you an example, and I think I wrote down that example as an application of what a partial derivative is. Let us say there's a disease and you want to find the effect of a particular drug on that disease. Okay, you may, in order to test the effect, you may have to keep certain variables constant, right, while varying the amounts of the drug. Okay, so maybe you may, one of the constant things that you may have to keep constant is possibly the environment that the person is in, the temperature, depending on the drug. Maybe you'd have to keep constant what that person eats and vary the drug. Okay, so you're finding the rate of change of the quantity of the drug on that disease, all right, and keeping variables constant. That rate of change is called a partial derivative. So the process for determining the rate of change of a function with respect to one of its independent variables is called partial differentiation. Okay, so with partial differentiation, you must hold some variables constant and differentiate with respect to another variable. So whatever you are differentiating with respect to must vary, but everything else must be looked at as a constant. That is partial differentiation. It's partial. So the result is referred to as the partial derivative of the function with respect to that variable. The partial derivative of the function, you can also refer to the partial derivative at the rates of change of f in the positive x and the positive y direction. So basically, if you have a function of two variables, x and y, you have to find two partial derivatives with respect to x and with respect to y. Of course, there is a definition of a partial derivative. So recall the definition of the actual derivative that you learned in single variable calculus. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. The definition of the partial derivative is much like that. It contains limits, but you have to look at holding certain variables constant. So let's look at the partial with respect to x. So let's say you have a function of two variables, x and y. And we want to partially differentiate with respect to x. That means you keep y constant. So if you look at y as a constant, then you have the derivative with respect to x. And look at the notation for the partial derivative of f with respect to x. F sub x like that, or partial f partial x, or partial z partial x. And this is the definition. It's the limit as h approaches 0. So as you can see, f of x plus h, because x has to, and just y is a constant, so that you don't have y plus h. You are differentiating with respect to x. So leave y alone, minus the function over h. And of course, if you want to do it with respect to, with respect to x at a point, you would have to substitute a for x and b for y. Similarly, the partial of f with respect to y is the same thing. Here are the notations for it. And the definition is you vary, you keep x constant, and because you differentiate with respect to y here, you have y plus h. Any questions on that? Okay, then let us do some examples. And of course, here is the partial derivative with respect to y at the point A and B. Okay. So we're going to actually start by using the definitions, but you know what's going to happen next. Afterwards, you're not going to use the definitions at all. That's how you started differentiation some time ago. Right, so I'm going to show you how to use the definitions to find the partials with respect to x and y. Okay, so let me write the definitions again. So let me write, we want to find first with respect to x, so write down the definitions. So you can put the partial z with respect to x. Make sure you put a curly D like that, okay? Do not put it straight like that. Because if you put it straight, that is the actual derivative from single variable calculus, okay? So put a curly, and this is equal to the limit as h approaches 0 of f of x plus h y minus f of x y over h. Let's work that out. That is equal to the limit as h approaches 0. So f of x plus hy means wherever you see x in the function, put x plus h. So this becomes x plus h all squared y minus the function is x squared y over h. Now that's limits, so all you're going to do is to simplify the numerator. You know, maybe you might have to factor out an h. Let's see what we're going to get. Okay, so when you do FOIL in this, you have an x squared and you have a y. So x squared y. The middle term, x times h times 2 times y. So that's plus 2xhy. The last term is h squared, and you multiply it by y. So that's plus h squared y minus x squared y all over h. So the x squared y's are going to cancel. You have left 2xhy plus h squared y over h. We can now factor out the h from the numerator. H times 2xy plus hy over h. The h's cancel, and then substitute h equals 0. The answer is 2xy. Okay, so that's the first one. Any questions? Now let's do it with respect to y now. So let's write out the definition. I hope I have some space here. So partial z, partial y, limit as h approaches 0 of f of x y plus h minus f of x y over h. So this is equal to the limit as h approaches 0. Now f of x y plus h says you just, in place of y in the function, you are going to put y plus h. So the function is now going to be x squared times y plus h minus the function itself is x squared y over h Now simplify this, x squared y plus x squared h minus x squared y over h. Okay, let me go over here. That's equal to the limit as h approaches 0 of x squared h over h. The h's go, you're left with x squared. Any questions? Okay, let's move on. Number 2. Okay, so this one has a little bit more in it. Alright, so this is going to be a little long, so I am going to write, we'll see, I might be able to put everything in there. Okay, so we want to find the partial with respect to x, and then we want to find the partial with respect to y at 0, 1. So again, let me write out the definition for partial with respect to x. So that is equal to the limit as h approaches 0 of f of x plus h y minus f of x y over h. This is equal to, so f of x plus h, put x plus h in place of x in the function. So that's 2 times x plus h all squared minus x plus h times y plus y squared minus the actual function put in parentheses because signs are going to change. And this is all over h. Oh, did I forget my limit? Thank you. Here. Let's simplify that now. So that's an x squared times 2. So, oh, I'm keep on forgetting this limit thing. Limit. 2x squared. Middle term is 2xh times 2. That's 4xh. H squared times 2 plus 2h squared minus xy minus hy plus y squared minus 2xy plus xy minus y squared all over h. When we simplify this, we have 4xh plus 2h squared minus hy over h. You know what to do now. Factor out the h. 4x plus 2h minus y over h. Cancel the h's, and this is 4x minus y. Because h approaches 0, so the 2h would go to 0. Let's do the partial with respect to y. What we will do, let's write out the definition first, okay? Not at 0, 1, let's just write it out generally. So fy is the limit as h approaches 0 of f of x y plus h minus f of x y over h. Now it's at 0, 1. So now rewrite the definition at 0, 1. So what you're going to do is that you're going to put 0 for x and 1 for y. So that's the limit as h approaches 0 of f of 0, 1 plus h minus f of 0, 1 over h. Okay? Now you're going to use the function that you are given with. Any questions so far? So let's substitute. So f of 0, 1 plus h. So in the function, put 0 for x and 1 plus h for y, right? So we have no first term, no second term, but we'll have 1 plus h squared minus f of 0, 1, put 0 for x and 1 for y. This is just a 1 over h. Simplify. Limit as h approaches 0. 1 plus 2h plus h squared minus 1 over h. Simplify. Put your limit. 2h plus h squared over h. Factor out the h. H times 2 plus h over h. Cancel the h's. You are left with 2. Two plus h, but your h approaches 0, so the answer is just 2. Yes.
I'm kind of lost on how we went from f of y 0, 1 right down to plugging it in. Where it's 1 plus h squared minus 1 over
Okay, let's write out the. Let me write out the function close by here. So f of x y equals 2x squared minus xy plus y squared. Okay. So you want to find f of 0, 1 plus h. Well, that means in the function, put 0 for x and 1 plus h for y. Got it? So you'll have no more. These terms would go, but you'll have 1 plus h squared. Good. Any more questions? So that's finding partial derivatives from first principles. Okay, why don't you try this one? So number 3, all I want to do is to find the partial with respect to x. That's all. So try that one. Okay, let's go over it. So partial z with respect to x is the limit. Always write the formula up front. It's going to help you. Okay, so the first one becomes x plus h times y squared minus the function over h. Distribute xy squared plus hy squared minus xy squared over h. You are left with hy squared over h. The h's go, which gives you y squared. Well done. Any questions? Okay, so these are partials from first principles. Now let's actually partially differentiate some functions just using rules, okay? Not from first principles. So note, unless I ask you to partially differentiate from first principles or using the definition, please don't do that. Don't use that. That's too long, okay? You just want to use the rules. So let me explain the rules. So we're computing algebraically the partial derivatives. And if you see here, I said compute all the first partial derivatives. So if the function has a function of 2 variables, there are 2 first partials. If the function has 3 variables, there are 3 first partials, and so on. Okay? So what is the rule of thumb? If you're partially differentiating with respect to x, that means you want to hold the y constant, right? So think, if you want to think of it this way, think of the y as a number, all right, and differentiate and apply all the rules that you have learned before. If you think of the y as a number, as a constant, then the function reduces to a function of one variable, x, so you can differentiate. Similarly, if you're partially differentiating with respect to y, you want to hold the x constant. So think of x as a number, so the function is going to be a function of y and differentiate. So let's do some examples. Number one, so we have done this before, but we're doing them algebraically without the definition. So let's go partial z, and I'll use different notations to get you accustomed, okay? Partial z with respect to x means hold the y constant. So imagine that the y is a number there, right? So therefore, when you differentiate with respect to x, you're going to get 2xy. With respect to y means x squared is going to be a constant, right? So when you differentiate with respect to y, you get x squared. Any questions on that? No, that's not a product. Don't think of product rule yet. No, we're in functions of two variables. Okay, so we are part of product rule that we partially differentiating. Let's do number 2. Fx, f sub x, partially differentiated with respect to x means hold the y constant, right? What do you think it's going to be? Just y squared. Beautiful. Partial with respect to y means hold the x constant. So what is it going to be? 2xy. Very good. Let's do number 3. We have two partials, two first partials to write down. Partial of f with respect to x. So all the y's are going to be constant. Differentiate x to the fourth. What do you get? 4x cubed. The next one, minus 3x squared y. The next one, 2xy squared. The next one, minus y cubed. What about the last one? 0, nothing, because y is a constant, yeah? When you differentiate a constant, you get 0. Next one. Partial of f with respect to y means all your x's are now going to be constant. Differentiate the first term, what do you get? 0. Good. Next term. Minus x cubed only. The next term with respect to y, plus 2x squared y. The next term with respect to y, minus 3xy squared. The last one with respect to y, plus 4y cubed. Excellent.
I have a question.
Yes.
With the first one, we got the last two terms minus y to the third, and then plus 0. Why is it that the y to the third stayed and the plus y to the fourth disappeared?
No, we have differentiated. You were mixing things up here. We have already differentiated to get minus y cubed. We're not differentiating y cubed. When we differentiated minus xy cubed, we just got minus y cubed. You're mixing things up here. Y to, very good. Y to the fourth, the derivative of that would be 0 with respect to x. Because there's no x attached. There's an x attached to the y cubed.
How does that change it?
It changes it because now you differentiate it now with respect to y, so you need to leave the x. Let me give you an example, right? If you had to differentiate 5y cubed, right? No, that's the wrong one. Let me take that. I don't like that one. Sorry, change. If you had to differentiate minus 4x with respect to x, what's the answer? Negative 4.
Okay.
So same thing here. Minus xy cubed. So think of y cubed as a 4. It's a number. Because you are partially differentiating with respect to x. So anything that is not x has to be a constant. That's the rule of thumb. Let's do some more. Oops. Okay, number 4. So remember, when we see these things, you would need to write it as 4xy to the minus 5. Right? We're not using the quotient rule here. You will see when you have to use the product and the quotient rule in a little while, okay? Partial z with respect to x. Tell me what that is. One person. Very good. 4y to the minus 5. Another person, give me the partial of z with respect to y. Negative 20xy to the negative 6. Beautiful. Great. Let's continue. Number 5. Partial of f with respect to x. So that is where you need to think of chain rules. You need to think of what happens when you differentiate the exponential function, e, right? So what do you get? You get the same thing, right, upon derivatives, right, upon differentiating. But it's a chain rule, so now you need to multiply by the partial of xy cubed with respect to x, which is y cubed. So your answer is just 3y cubed e to the xy cubed. So you see the chain rule is now coming into effect here. Partial of f with respect to y. It's the same thing, 3 to e to the xy cubed, but what do you multiply by? 3xy squared. We're partially differentiating xy cubed with respect to y. So this gives us 9xy squared e to the xy cubed. Number 6 is similar to that. Let's do it. Partial f with respect to x. So you have e to the x squared plus y squared. But what do I multiply this by? 2x. Good, because you are partially differentiating x squared plus y squared with respect to x. So can somebody tell me what is the partial of f with respect to y now? 2y, e to the x squared plus y squared. Great. Any questions so far? More. That's another chain rule now. Z equals sine of x squared plus y cubed. So let's do it. Partial z with respect to x. Differentiate sine, you get cosine x squared plus y cubed. But we need to multiply by 2x, which is the partial of x squared plus y cubed with respect to x. So that's 2x in front. Can somebody tell me what now is the partial of z with respect to y? What goes in front now? 3y only? 3y squared. Cosine of x squared plus y cubed. Beautiful. There's some more. Now, if you notice in number 8, you have 3 variables, right? So that means you're going to have 3 first partials. Okay, so let's do it. The partial of w with respect to x. This is another example of the chain rule, right? When you differentiate the natural log function, you get 1 over this entire thing, but you multiply by 3x squared. Very good. So this is 3x squared over x cubed plus y squared plus z. The others are going to be similar, but just remember what you multiply by. Partial w with respect to y. The same thing, but what goes on the top? 2y. Good. Partial of w with respect to z. The same thing, but what goes on the top? Just 1. Great. Any questions so far? So if you've noticed, so far we've done some basic partial differentiation. We have used the chain rule. We haven't used products and quotient rule yet, right? Let's continue. Maybe it's coming up now. No, it's not. But let's do that. So, partial of f with respect to x. This is another example of the chain rule. So, you differentiate tangent inverse. So, remember, when you differentiate tangent inverse, you get 1 over 1 plus whatever this is, y over x all squared. Right? Times, you need to now partially differentiate y over x with respect to x. Who can give that to me? Negative. Let me write that there. Y over x is y x to the minus 1. Agreed? Now partially differentiate. Negative. Y. Exactly. Now you know we have to simplify that, right? So I don't have much space, so let me write that there. So let me simplify this first fraction here, complex fraction. So this is 1 over 1 plus y squared over x squared. And I'm going to write this as minus y over x squared. To simplify that complex fraction, I'm going to multiply everything by x squared. So get rid of this stuff here. So you have x squared at the top over x squared plus y squared. That works out really nicely. Times this minus y over x squared. Cancel. You have minus y over x squared plus y squared. So that is the partial with respect to x. Now let's go for the partial with respect to y. So the partial with respect to y, you start off the same way. 1 over 1 plus y over x all squared times what? Partially differentiate y over x with respect to y. What do you get? X to the minus 1, right. Simplify that again. So this is x squared over x squared plus y squared times 1 over x, which works out to be x over x squared plus y squared. Now look at number 10. Number 10 is an example of the product rule. Why? Because you have two functions, the product of two functions, this one, and both of them are functions of x and y. Now you have no choice but to use a product rule. Okay? So let's do it. So partial of f with respect to x, remember the product rule. Differentiate the first with respect to x. What is it? 2x times the second, tangent inverse of y over x, plus, leave the first alone, times the derivative of the second with respect to x. Now we just did this up there, right? So we got minus y over x squared plus y squared. So this leaves us with 2x tangent inverse y over x minus y. Done. Any questions on that? Because that was the product rule. Let's do this. Let's do the other one now. The other first partial, f with respect to y. Do the same thing. What is the partial derivative of the first function with respect to y? 2y times the second plus the first times the second with respect to y. We just did that to get x over x squared plus y squared. And this leaves us with 2y tangent inverse y over x plus x. Sweet. Now you know we have done the product, so you know the quotient is coming up, right? I hope. Let's see. Yeah. I've changed the variables to r and s. Don't be dismayed. You will now have the partial with respect to r and the partial with respect to s. Okay? Now how do I know that I have to use the quotient rule here? Because it's a quotient and the numerator is a function of r and s. The denominator is a function of r and s. That's why. Okay? So let's do it. The partial of f with respect to r. Quotient rule. Partially differentiate the numerator with respect to r. What do you get? 2r times the denominator minus partially differentiate the denominator with respect to r. What do you get? 2r times the numerator all over the denominator squared. Simplify. 2r cubed plus 2rs squared minus 2r cubed plus 2rs squared all over r squared plus s squared squared. So we get here 4rs squared over r squared plus s squared squared. That is the quotient rule. Any questions here? Let's partially differentiate with respect to s now. The partial derivative of the numerator with respect to s is what? Minus 2s times the denominator minus the partial of the denominator with respect to s is 2s times the numerator all over r squared plus s squared all squared. Simplify. Minus 2sr squared minus 2s cubed minus 2sr squared plus 2s cubed all over r squared plus s squared squared. And this leaves us with minus 4sr squared over r squared plus s squared squared. Now I think it's your turn.
Oh no.
I think you have about 4 to do. Do it. Let's do it. Easy like squeezy.
Something like that.
Okay, let's go over it. One person, number 12, give me the partial with respect to x, please. Negative 3y. Somebody else give it to me with respect to y. Very good. Number 13, one person give me partial with respect to x, please. And give me the work, because it's a chain rule here. Very good. Very good. Somebody else give me partial with respect to y. Great. 14. One person give me the partial of f with respect to x, please. Yes. 1 over y or y to the negative 1. Another person, give me the partial of f with respect to y, please. Great. You can leave it so, that's fine. Any other questions so far? Okay. Now, we have partial with respect to p and q. So you need to give me the work for that. One person, what is the partial of r with respect to p, please? Working.
1 over 1 plus 3q squared times q squared.
What are you doing with this? All of that must be squared, right?
Yeah.
Times what?
Q squared.
Q squared, good. So this is q squared over 1 plus p squared q to the 4th. Somebody else give me r with respect to q, please. Times, tell me again? 2pq, very good. So that's 2pq over 1 plus p squared q to the 4th. Any questions? Don't do that. Don't do that because there's a plus in between. You cannot just cancel this. Okay. Any questions? Let's continue. Let's look at now differentiating implicitly. You can't do that in multivariable calculus. So in order for you to remember or to know how to do that, you need to remember how you did that in single variable calculus. Okay? So let's look at an example from single variable calculus. Find the y dx where x squared plus y squared is y. So remember how you did that before was that you looked at y as a function of x. Okay? So you differentiate term by term. So differentiate x squared, you get 2x. Differentiate y squared, you get 2y. But because y is a function of x, you needed to multiply it by dy dx. It's something like the chain rule. Multiply by the derivative of the inner function, equals differentiate y, which is 1 times dy dx. And you just solve for dy dx. So you'll have 2x equals dy dx minus 2y dx. Factor out the dy dx. 1 minus 2y. And so this tells us that dy dx is 2x over 1 minus 2y. So that's how you did it in single variable calculus. Do you remember that? Okay, it will come back to you for those who don't. So, what happens in multivariable calculus? What happens if functions of two variables or more than one variable? You treat z, for example, if it's two variables, treat z as a function of x and y. So you differentiate or you partially differentiate each term. But when you reach the z, make sure you multiply by the partial derivative. Okay, so let's do some examples. We want to find the partial of z with respect to x and y. Now, sometimes you may not need to use implicit differentiation. If you can solve this equation for find what z is, you can just use what we did before. But sometimes it is difficult to solve for z. So it would be better for you to use implicit differentiation. Okay, so let's first find partial of z with respect to x, okay? So with respect to x first. With respect to x. Okay, so let's go. You are going to partially differentiate each term. So partially differentiate x squared with respect to x is 2x. Partially differentiate 2y squared is 0 because it's a constant. Plus, now partially differentiate 3z squared is 6z, but we need to multiply it by partial z partial x equals partially differentiate 1, you get 0. So solve 6z partial with respect to x is 2x. So partial with respect to x is 2x over 6z, which is minus x over 3z. So that's that one. Yes. That's right. Sorry about that. So I did it here, but I didn't. Yeah, thanks. With respect to y now, let's do the same thing. Partially differentiate with respect to y. The first term, the partial derivative is 0. The next term is 4y. The next term is 6z times partial of z with respect to y, and this is 0. So partial z with respect to y is minus 4y. I'm missing, okay, I'm doing too many steps at once. So let me put a 6z here. So this tells me that partial z with respect to y is minus 4y over 6z, which is minus 2y over 3z. Questions? Okay. Let's do some more. So we want to do the same thing. So let's go with respect to x first. Now I want you to notice something, right? The first term is y times z. You have to use the product rule here. Okay, because you have y and you have z, which is a function of x and y. Good? The second one, don't bother to use the product rule there, and that is what people get confused in, because you have a product here, but they are not both functions of x and y. Okay? Alright, so let's do it. So yz, we want to partially differentiate that with respect to x, right? Product rule. Partially differentiate y with respect to x is what? 0, right? So the first term is going to be 0. I'm going to write it because I need you to see where we're going. Plus, we're still on the first. Hold the y. Partially differentiate z with respect to x is partial z partial x. We finish with the first term, yz. Next. Partially differentiate x natural log y with respect to x. What do you get? There's a natural log of y. Equals. Partially differentiate z squared with respect to x. You have the 2z, but you need to multiply by partial z partial x. Okay? Now we need to solve here. Alright, so we have natural log of y on this side, and then we're going to have 2z partial with respect to x minus y partial with respect to x. Factor it out. Partial with respect to x times 2z minus y. And so partial with respect to x is natural log of y over 2z minus y. That's that one. Any questions on that before we do with respect to y? With respect to y. Again, yz is a product. We need to treat it as such, right? So, partially differentiate y first. We get a 1 times z, that's a product, plus hold the y and partially differentiate z with respect to y, you get partial z partial y. Next term, x natural log y plus, what is the partial with respect to y here? Anybody can tell me? X over y, very good, because when you differentiate natural log, you get 1, right, over y. And then z squared now. What do we get here? When you partially differentiate z squared with respect to y, what do we have? 2z and what else? Partial z partial y. Okay. Now, let's try to see what we can do with this. We're going to solve. So, the left side, I have z plus x over y. And then on the right, I have 2z partial z partial y minus y partial z partial y. And you know what to do, factor. So, z plus x over y is partial z partial y times 2z minus y partial z partial y equals z plus x over y over 2z minus y. And I would simplify this fraction a little better. We have a complex fraction there, so there's a denominator of y here. So I would multiply every term there by y. So this is yz plus x over y times 2z minus y. That makes it look a little nicer. So that is implicit differentiation. Any questions? Okay. Now we're going into higher order partials. For the purpose of this course, we will just go into the second order partials. So what we have done so far are the first order partials. When you differentiate or find the partial again, then you'll have the second order partial. We will not do the third or the fourth. We're not going there, okay? So let us look at the definitions of these second order partial derivatives. So if z has a first order partial, fx, and if fx also has a first order partial with respect to x, this is denoted by fxx. Okay, so f(x) means you are partially differentiating f with respect to x twice. And I've given you the notation. So another way of writing fxx is this notation here. But usually the fxx is used more often. Similarly, fyy means you partially differentiate with respect to y twice. Then there are others now. What if you partially differentiate with respect to x and then you partially differentiate with respect to y? Then you have fxy. So you do the x first and then the y. If you do the y first and then the x, then you have fyx. And that is a notation for it. Now there's a very important theorem called Clairaut's theorem, which tells you that fxy and fyx are usually the same if there is continuity. If they are both continuous, then they are the same. Okay? And this theorem is going to help you quite a lot later on. Right, so let's do some second order partials. So you know that for you to find second order partials, like you did for single variable calculus, you have to find the first order. Okay? So this is asking you in number 1 to find the second order partials. You need to find all. So first, let us find the first order partials. So can somebody give me, one person give me the partial of f with respect to x? Mm-hmm.
Minus
Good.
8x.
Excellent. Excellent. So as the partial of f with respect to x. Now let's deal with this. Let's now find fxx. That means we are partially differentiating fx with respect to x. Can another person give me that, please? Mm-hmm. Very good. Let's go further. Let's find fxy. What are we doing? We're taking fx and partially differentiating it with respect to y. Can another person give me that, please? minus 16xy. Beautiful. All right, so that's the fx. Now let's find the first partial with respect to y now. Can somebody give that to me? Mm-hmm. Very good. Okay, let's continue. Can somebody else give me fyy? So that means you're taking fy and partially differentiating with respect to y. What's that? 12y squared minus 8x squared. Any questions so far? And then finally, I want to find fyx. So, can somebody partially differentiate fy with respect to x? Can somebody give me that, please? And as you can see, they are the same because this entire function, f of xy, is continuous. It's a polynomial. Any questions?
So if they are equal, it is continuous?
Yes. Now, yes, yes. They're equal because it's continuous. That's good. Let's do this one together again. Let's find the first partials. Can somebody give me fx? And note that this is the chain rule. Okay, who's going to give me that? It's a chain rule. What do we have? 2xy cubed.
Times cosine x squared y squared.
Cosine x squared y cubed. Beautiful. Okay, so the derivative of sine is cosine and partially differentiate x squared y cubed with respect to x. Right? Okay, let's do fxx right away. Now look at this closely. This is a product. We have to use the product rule here. Good? Because we have this and that. Functions of x and y, both of them. So let's use the product rule. Partially differentiate the first with respect to x. You have 2y cubed times the second plus leave the first times partially differentiate the second with respect to x. We have a minus sine x squared y cubed times the partial, which is 2xy cubed. Let me just write this a little better. 2y cubed cosine x squared y cubed minus 4x squared y to the 6th sine x squared y cubed. So that's fxx. We go in fxy now. Do the same thing. Partially differentiate 2xy cubed with respect to y. Now these questions are not difficult, but they can be tedious. And you can make an error very quickly. So you really have to concentrate, okay? Okay, 2xy cubed with respect to y is 6xy squared times cosine of x squared y cubed plus leave the 2xy cubed times partially differentiate the cosine with respect to y. So that's minus sine x squared y cubed times 3x squared y squared. That's correct? Okay, so that's 6xy squared cosine x squared y cubed minus 6x cubed y to the 5th sine x squared y cubed. Okay, so that's fx. Let's move on to the first partial with respect to y. Any questions so far? Okay, first partial with respect to y. Who wants to give that to me? Mm-hmm. Good. Again, this is a product. So, we need to use a product rule here. So let's do fyy. So, partially differentiate the first with respect to y. 6x squared y cosine x squared y cubed plus 3x squared y squared times minus sine x squared y cubed times 3x squared y squared, which works out to be 6x squared y cosine x squared y cubed minus 9x to the 4th y to the 4th sine x squared y cubed. Now we want fyx, and if we do not get the same thing as fxy, we have made an error, because that is a continuous function. Fyx. We are partially differentiating fy with respect to x. So the first term will give us 6xy squared times cosine of x squared y cubed plus 3x squared y squared times minus sine x squared y cubed with respect to x, which is 2xy cubed. So this is 6xy squared cosine x squared y cubed plus, no, minus minus 6x cubed y to the 5th sine x squared y cubed. And that's what we got. Okay? Any questions? Okay, so it's your turn, number 3. Find all the partials, the first and the second. Okay, let's go over it. Can one person give me partial of f with respect to x, please? One person. Very good. Some other person continue with fxx. Another person continue with fxy.
6y plus 20xy.
Good. Another person give me the first partial with respect to y. Very good. Another person give me fyy. Good. Another person give me fyx. 20x only? Yeah. Okay, and as you can see, they're the same. Why? Because f of xy is a continuous function. It's a polynomial. Let's look at an application. It's just an application. When I say application, it's just to ensure that you know how to use that these first and second order partials, that you can find them. The Laplace operator is defined by this. It is really the sum of fxx and fyy. A function u of xy satisfying the Laplace equation, Laplace u or delta u equals 0, is called harmonic. Show that the function is harmonic. The function u of xy equals e of x cosine y. What is the question asking us? We need to show that the function is harmonic, what you need to show is that delta u is 0. That's what you need to do. But what is delta u? Is the sum of the partials uxx plus uyy. So that is, we need to show that uxx plus uyy is 0. Okay? So all we need to do is to find these two and see if we get 0. So look at the function. We need to get ux. So e to the x cosine y, what is the partial, the first partial of this with respect to x? Very good, that's all. And again, partially differentiated with respect to x, we get the same thing. Okay, so that's uxx. Now, give me the partial of u with respect to y, anybody?
E to the x times minus sine y.
Negative sine y, so that's minus e to the x times sine y. Good. And then give me uyy, partially differentiate uy with respect to y. What's that? What's it? Negative e to the x, what else? Cosine y. And as you can see, and uxx plus uyy, that is clearly nothing. Okay, is that it?
Yes, sir.